Okay, so the last talk of this session is some more cryptanalysis. So it's called Opening the Black Box, Collision Attacks on Round-Reduced Tip 5, Tip 4, Tip 4 Prime, and Monolith. And Fukang will give the talk.
Yeah, thanks for introduction. This is a joint. I'm Fukang. This is a joint work with Casalina, Lorenzo, Len, Siyao, Shabhadip, and Vidi. So first, let me give a very brief description of the tip 5 family. So the tip 5 permutation is defined over a prime field. So, and the prime is this value. So it's a 64-bit prime number. As shown in this figure, the state size is composed of 16 field elements. And I mean, it's a very common design based on the sponge structure. But you should note that the nonlinear layer is very special because there are two types of substitution boxes, which we call the S box, the one colored in gray, and the T box, where the T box is simply the power map x2 to the 7. I will not give the details of the S box first. I mean, basically, in the last talk, you should know what it looks like. But what I want to emphasize here is that this S box will correspond to a very complex and high polynomial of OFP. And for the hash function tip 4, it's based on the same permutation as tip 5, but the parameters for the sponge is changed. So yeah. And for tip 4 prime, again, no, not the same permutation, because the state size is reduced from 16 to 12. And the parameters for the sponge is changed accordingly. So yeah, it's here. But there is a common feature. So in each round, there are 4 these special S boxes here. So what does monolith look like? Basically, it's again similar, but the main difference exists in the nonlinear layers. You can see here there are 2 consecutive nonlinear layers in each round, and the first nonlinear layer is indeed a partial nonlinear layer. For example, for the case of monolith 31, the first nonlinear layer consists of 8 S boxes, and then the second nonlinear layer is just a phase tail like transformation via a quartic function. So basically they are the same, but just how to place these special S boxes. And so how to attack this kind of ciphers with some special S boxes, which will correspond to a high degree and complex polynomials, OFP. And if P is large, we even cannot write down what the polynomials are. And I also summarize some differences here. And one notable difference between tip 5 and monolith is the exists in the very beginning. So you can see that in the very beginning, there is a linear layer in monolith, but you can note here there is no linear layer at the very beginning. Yeah. So how to analyze such ciphers? Yeah, in our paper, we propose 2 attack frameworks. The first one is the 2-stage attack framework. It's very efficient for 3-round tip 4, 2-round monolith 31, but it's not very efficient for 3-round tip 4 prime. But I will describe why it is efficient for tip 4 prime, and you will also know why it's efficient for tip 4 or monolith. So the idea is indeed very simple. We just we just want to skip the influence of these special S boxes. So since there's no linear layer at the very beginning, we can start from the input of the second round. So just, yeah. And specifically, we can choose all the 4 S boxes to be active. And we also set one additional T box as active, while the remaining 70 S boxes are all inactive. Then, in the backwards direction, we want to ensure there's no difference in the inner part, which will correspond to 4 linear equations in delta x0 to delta x4. And in the forwards direction, we want to ensure there's no active S box at the third round. This will again correspond to 4 linear equations in delta y0 to delta y4. So it's easy to get a candidate of delta x, delta y, but not every solution is valid because delta xi, delta y is the input and output difference of the S box. So we need to check whether it is a valid difference transition. I will describe how a main technical contribution of this work is to solve this problem. How to know that xi, that y is a valid difference translation, but I will describe it later. Let us assume we have this algorithm, and we also have the algorithm, and assume we also have the algorithm to find the right input pairs if it is a valid difference translation. So then it should be clear that the complexity of this state is directly related to the probability that a random input-output difference is valid for this S box. And after stage 1, we will fix all the input pairs of the first file boxes at the second round. Then we are left with 7 inputs to the remaining 7 T boxes, and we set them as unknown variables, x5 to x11. Now we want to have a clean. So first, in the backwards direction, we need to match the inner part because it's fixed. This will correspond to 4 linear equations in these 7 unknowns. And in the forwards direction, since the S box in the third rounds are inactive, we know its output difference. So we can write the difference in the hash value as polynomials in these unknowns. And we can upper bound the algebraic degree of these polynomials as 32. A trivial bound is indeed, no, 42. A trivial bound should be 46, but we can show it's indeed 42. But this is not bad, but this is indeed bad because the system is overdefined. We have a solution with probability 1/2, so we need to repeat the attack p times. This is bad. But this problem will not occur in the attacks for T4 because you can see finally at stage 2, the system is underdetermined, which means we can always expect a solution. And the scale of the polynomial system is not too large, so we can solve it. It's not too time consuming. And for monoliths, similarly, we can apply a similar idea. So we also do not have this problem because the system is well defined. So we have the same number of equations and the number of variables. So as you can see, the main problem in the clean attack on T4 prime is the insufficient degrees of freedom. So how to save the degrees of freedom? So that's why we propose the 3-stage clean attack frameworks. So we will use multiple message blocks. So compared with the 2-stage framework, we have an additional stage called stage 0. So we will use additional message blocks to generate a random pair of the inner part, like E0, E3, E0 prime, E3 prime. Then then the inner part, the difference in the inner part is no more 0. And the stage 2, stage 1 it's similar, but there are some differences. So first, at the second round, we only activate the 4 S boxes. So all the T S boxes are set as inactive. And in the third round, we allow 1 S box to be inactive. But we fix this input-output difference in advance. So after stage 1, after we finding such an input-output difference delta x, delta y, and as well as the corresponding right input pairs, we can move to stage 2. Then the system becomes well defined because the number of equations is the same as the number of variables. But it does not mean the solution is always valid because we need to check whether the differential transitions through this active S box at the third round is valid. So we again need to repeat it. But if the differential transition probability is high, then we only need to repeat the attack a few times, so which is good. So there are some central problems to make our attacks framework work. So it's all about this black box, this box. So what does this S box looks like? So let us check it. So you can see this figure. I will not give a general description of this S box. Let's just take the tip 5 S box as an example. So we denote the input and output of the S box by W and Z. So WZ are both 64-bit values. And to compute Z, we first decompose Y, W, as 8 bytes, W0 to W7. Then each WI will pass through an 8-bit permutation SI to get the corresponding output ZI. Then the 8 bytes Z0 to Z7 will be composed to form Z. Then we get the output Z. To ensure it indeed we can prove it is a permutation over FP, we just need the first 3 conditions. I mean, 0 is mapped to 0, O1 is mapped to O1, and the SI is a permutation, and P is takes this value. So you can prove very easily. So recall that our main problem to make our attack framework is to determine whether a differential transition is valid, and if it is valid, how to find the right input pairs. Okay, that formally we can write it in this way. So how to do it? So given the input difference delta W and the output difference delta Z, of course we can decompose them as 8 bytes. So we can get delta WI, delta ZI, but with delta ZI and delta WI, we do not really know the relations inside the input pair, WI prime, WI, or the output pair, Z or ZI or ZI prime. This is an example. So remember that W prime equals to W plus delta W modulo P. So, and it's also not easy to, it's not difficult to imagine where the problem comes from. It's indeed caused by the modulo P operation and the carry between the bytes when computing W plus delta W modulo P. So our first to solve to solve this differential equation given delta W delta Z, we first try to remove the influence of the modulo P operation with a simple trick. So let us consider x prime equals to x plus delta x, where x prime, x delta x are all smaller than P. Then there are 2 possible cases. The first case is x prime is larger than x. Then in this case, we indeed do not do the modular addition. So x prime is just the x plus delta x. But if x prime is smaller than x, then the modular addition is performed. So indeed we have x prime equals to x plus delta x minus P. So this can be rewritten as x equals to x prime plus P minus delta x. But we can let B minus delta x as delta x bar. Then we can have these 2 equations according to the relations between x prime and x. And these 2 additions are all over the integer of range, which means we do not need to care about the modular operation. So we have removed its influence. Now, again, let us recall the problem. We want to solve this differential equation given delta W and delta Z. So, and let us, so the problem can be restated that we have an input-output pair of the S-box WZ and another input-output pair of the S-box W prime, Z prime. How to find how to find a W prime, Z prime satisfying the 2 equations? So according to our analysis, we want to remove the influence of modular P. So we don't want modular P here. So we guess the relations between W prime and W, Z prime and Z. So we have in total 4 cases. And for each case, if we can find W, such that this, for example, if for case 1, if we can find W equals to W prime plus delta W bar, Z equals to Z prime plus delta Z bar, then we find a possible solution to W, and we just proceed case by case to find all possible solutions of W. The problem can be restated with some simple symbols. So we are given a delta and a lambda, and we are given 2 input-output pairs of the S-box, A, B, A prime, B prime. How to find all possible solutions of A satisfying one of the following specific cases. These cases can be related to these 4 cases. For example, in case 1, we set delta W bar as delta and delta Z as lambda. So then we just solve this equation. So how to solve it? It's very similar. Okay. So let us take the case 1 as an example. So in case 1, we have A equals to A prime plus delta, B equals to B prime plus lambda. No modular addition is required here. So we can proceed the byte. So the ith byte, we can proceed the byte, each byte in a similar way. This is a very simple method. It's not written in our paper. So we can first guess the carry CIRI. Then we guess AI. With CI delta I known, we can calculate AI prime and the corresponding carry to the next byte, CI plus 1. Then if AI and AI prime is known, we can know the output BI and BI prime. But note that B equals to B prime plus lambda. So we need to check whether this equation holds. If correct, then we get a right candidate. And also we can get the carry bit for calculating a B prime plus lambda. So it's easy to see there are many redundant operations. We can use the idea to build DDT to save the cost. So specifically, we have an offline phase. We can exhaust all possible delta I and the carry bit CIRI. The corresponding lambda I, and we store a candidate solution of these variables in this tuple in a table DI. With the table D0, D1, D2, D3 to D7, then given any delta and lambda, we can easily retrieve the value of A, satisfying the relation. So we just first we retreat the byte by byte from the least significant byte to the most significant byte. So note that at the very beginning, so the carry bit are all 0. So we can first retrieve A0, B0, C1, R1 for the given delta 0, lambda 0, 0, 0 with the table D0. Then we know C1, R1. Then we use it. Then we use delta 1, lambda 1, C1, R1, and use table D1 to retrieve A1, B1, C2, R2. Then we repeat this, we can get a full value of A and B. But finally, we need to check whether it's indeed in the final field FP. So we need to do some check. And for case 1, it's the same. We only need to change the relation. So because in case 1, we have B prime equals to B plus lambda, while in case 0, we have B equals to B prime plus lambda. So we just need to change here. And similarly, at the offline phase, we only need to change. We just exchange the place of BI and BI prime. So nothing too much changed. And similarly here, we only do just exchange the place of BI prime. So so the same method is very simple. So can be applied to case 2 and case 3. So we can find all solutions of A, satisfying. We solve this differential equation for any given delta W and delta Z. And with this method, we can also use it to estimate the differential probability that random input-output difference is valid. We just we use the 1 million random delta W delta Z, and we perform experiments and get some numbers. So we can find the differential probability. The last column. Again, it's not so low. So the complexity of our the complexity of stage 1 of our tech is not too high, and we can for the last second column in cost, we can see the algorithm to retrieve W is very efficient. It takes just a few number of table lookups. And we have the last problem. We want to find input-output difference of this S-box such that it holds with a high probability. And we can do it easily. So that's all. Thank you.
Are there any questions? A quick question. Did you try your attack on any other ciphers, or do you think this technique would work on some other targets?
Other ciphers, you mean? I mean, such designs are, I think it's very specific to such designs where there are two types of S-boxes, because the main idea is to skip this special S-box because it has a very high degree, and we do not want to consider.
Okay, thank you. So we can thank Fukang and all the speakers of the session.